What are the oldest rocks on Earth? I got to speak with two experts on this, and the answer might surprise you. So let's jump into this conversation about Earth's oldest rocks and how we date them.
I'm Dr. Jesse Remick. I'm a geology professor at Penn State University.
My name is Chris Bullheis. I am a high school geology teacher in the great state of Michigan.
Chris and I have run a podcast, PlanetGEO. We had you, we had Geo Girl on a couple months ago, I suppose, or whatever time this releases at. But we run a podcast called PlanetGEO that we've been running since kind of COVID days. We also have an audio conversational textbook app called CampGeo, where we have a whole bunch of content, basically audio with some visuals, with little bits of videos, little bits of imagery that goes along with the audio content. So podcasts, visual podcast series, basically is what we call them. So yeah. We talk about rocks and all sorts of stuff, all sorts of geology related stuff.
And Jesse is one of my former students. So
that's right. Yes.
Back in the day. That's right.
Chris taught me an unnamed number of years ago, taught me high school earth science, basically AP geology, field geology class that he teaches still to this day, going out western United States.
Yeah, I have to highlight that one, I just learned about you guys a few months ago when you guys had me on your podcast. And by the way, to the audience, I am obsessed with their podcast. I've been it's all geoscience related. It is every topic under the sun. It's amazing. And you guys have such great and constructive conversations about things that are also very simple to understand, which is incredible. And one thing that I just love so much is, Chris, your ability to explain things in a way that is understandable, because I mean, you have obviously experience teaching high schoolers, which when I first started teaching, especially on YouTube, I was so bad at talking. Like, I was so stuck in my own little research. I could not explain things simply. Yeah. And that took so much practice and so much learning. So I really appreciate y'all's just natural ability to do that, and in a conversation that's very interesting the whole time. So it's incredible, and I really applaud you guys for everything that you do.
Awesome.
Well, we appreciate that. Yeah. Any good analogies that I might use ultimately are stolen from Chris as well, just so that's clear. Yeah.
So I'm really excited about our conversation today, because today we are going to be talking about Earth's oldest rocks. And I have not, it's kind of crazy. I haven't touched on this on my channel yet. I have talked a little bit about dating old rocks. I've talked a little bit about some of the rocks that have the potentially oldest signatures of life. But I have not gone to the oldest extent of rocks, which you guys have many podcast episodes and audiobooks about. So I thought you guys were perfect to have on to talk about this. And this is going to be such an amazing conversation. But to start with, why is it important that we study Earth's oldest rocks? What's in it for us today?
Do you really want to get Jesse going on?
Yeah, I think Chris should lead off with this one.
Well, Rachel, why do you think it's important?
Well, I always say the past is kind of our key to the present and understanding progressions that might occur in the future. In my class, that's often directed at right now, climate, but it's true geologically and biologically, and that's why we study everything in Earth's past. So that's how I look at it. But I'm curious what you guys think.
This is something that I'm really passionate about, and I have been for a long time, is, it really goes back to just the whole age of the Earth thing. I don't know. I live in a very conservative area, and I come across this a lot then with my younger high school students, where, they question that. And so this is something that is really important. It's near and dear to my heart. And just from that philosophical standpoint, the Earth is old, and we need to learn about that. And how do we know this? I think it's just, like you said, it's important to know where we've come from, to know where we're going. And so just from that philosophical standpoint, it's a really close to my heart, important issue to tackle head on. But then also, we need to know about the early Earth and the way that differentiation took place on our planet, because that's really shaped our understanding of rare earth elements, where they concentrate, how they concentrate. And these resources are, you can't underemphasize how important that topic is for this kind of green transition that we need to pursue. So I don't know, Jesse, what are your thoughts on this?
Yeah, no, I think along kind of similar, those same lines. I mean, this is something I've frankly struggled with throughout my life. I remember having a beer with Chris on his porch. He's got this kind of log cabin home set back from the, in the woods. And we were having a beer on the porch talking about this when I was kind of finishing my PhD, Chris, I think was kind of the time frame. And yeah, I struggled with it, frankly. Like, what, am I going to dedicate my professional life to understanding more about the early Earth? This is like where I did my PhD in this stuff. I continue to have at least a third of my research portfolio is kind of working on this. And you have to validate that. And my validation is it's really planetary science. So why should we go explore Mars? Why should we go explore Venus? It's the exact same reason we should go explore the early Earth. Humans explore. And when we go back in time, especially really far, the ages we're going to talk about, it's pure exploration. We don't know what our planet looked like. We're getting little windows into planets that no longer exist, but the Earth used to exist. It produced these rocks. And so if we want to understand that full history of a planet, we need to continue exploring and finding more of these old terrains and studying them. And like Chris said, if you go back to what are called Archean cratons, big blocks of ancient crust, they host the vast majority of platinum group elements that we have mined from Earth. A lot of them are exposed in these terrains, big gold deposits, things like this. So like understanding those types of things is really quite important.
Yeah, absolutely. I always tell my students, or whenever I'm explaining this to anybody, I like to say that before humans are around to take climatic and environmental and other measurements of Earth systems, rocks were the people around taking those measurements. And that's why the rock record is so important, and understanding Earth's history comes from the rock record. And then understanding Earth's history, like you said, has applications for understanding the whole solar system's history, which we'll get into. But it's
can I ask you a question? I mean, you're exactly right. I think most people, the students that I teach, don't understand how much Earth has changed. They don't know that for half of Earth's history, there was like no oxygen in the atmosphere, very little at all. I saw your video on the banded iron formations, these extinct rocks, like those used to be really prevalent, and they tell something really fundamental about the Earth. So I think that's just cool that Earth has changed so much and kind of amazing. But my question is, what is the oldest rock you have in your collection that I see behind you a little bit? What's the oldest rock you have? And do you have a very old one? Because we could send you I could send you a piece of Acosta if you don't have a very old one.
No, really?
Yeah.
Oh my gosh. You guys.
Rachel, do you understand how special this is? He does not fart with Acosta very easily.
Well, but I have when we're up there doing fieldwork, we collect samples for like museums and showcasing and public science communication. And, the popularity of your website or the popularity of your channel certainly warrants that. So what is the oldest rock you have?
I only have maybe 1.3 billion years old.
Oh, a baby. Oh, yeah.
A baby.
I don't have anything that old.
Okay. All right. Well, we'll get you some old stuff. There we go. Perfect.
Oh my God. I'm so excited now. Oh gosh. This is exciting.
It's a big deal for Jesse to do this.
I remember listening to the podcast episode where you guys were talking about the sample that he gave you, Chris, and I was like, oh, so lucky.
So I actually have one of the oldest rocks on the Earth, and this summer went to Iceland and now have one of the youngest rocks on the Earth. It's just 2 months old. Yeah.
Yeah. Bookmark.
Wow.
That's so cool, isn't it?
That's totally cool.
That is really incredible. That's not a lot of people can say that.
No,
wow.
Hold them in your hands, stretch out your arms, and you got like 4 billion years in between the two of them. That's very cool.
Oh, that's so crazy.
Yeah.
Wow. This is okay. Anyway,
amazing.
I know we're going to keep talking, but the short answer is it's important. Okay.
Yeah.
So, and as we go through this, that'll become evident. But to kind of kick off our discussion about Earth, specifically about Earth's oldest rocks, I want to start with one that seems simple, but is actually not. That is essentially, we know Earth is around 4.5 billion years old. So Earth's oldest rocks must be around 4.5 billion years old, right?
Jesse, let's put a timestamp on the Acosta then.
Yeah. So the oldest rocks that we know of, the rocks that I studied that I'll send you a sample of, we know we have rocks 4.0 billion years, 4.02 precisely. We can go to more digits than that now, but they're 4.02 billion years old.
How do we know that Earth is 4.5 billion years old if the Earth rocks only go up to 4.02 billion years old?
Yes. Well, we look at other rocks in the solar system, and we have a lot of rocks from the solar system as well. So we can go to the moon. The moon has rocks that are older than most of the ones we have on Earth, 4.35 billion years old are kind of the oldest ones. Mars has some pretty old stuff, but the real data comes from meteorites. Meteorites where we can look and we can see not only rocky meteorites, what we call stony meteorites that look like planetary bodies, but iron meteorites that look like the interiors of planetary bodies. We can also look at things called chondrules, which are the first solids to condense out of the solar system. And there's some kind of complicated geochronometers that we can use to apply that and get an age of 4.5682. Basically is the best number
that's
you can
crazy.
come up with. But you get really,
every time you say that,
really
I love
precise. Yeah, we could get like plus or minus a million years.
Yeah,
and so we're that's a needle in the haystack that we're identifying very precisely.
Yeah, I love that aspect because I have so many people, whether it be in my comments or students, that are like shocked that the way we dated Earth's age is with non-Earth rocks.
Yeah.
I think it's a fun concept.
Well, I think it's important, like, we have to, because Earth is dynamic, and that clock, that radiometric clock, gets reset because of plate tectonics and melting and things like that, which doesn't happen to meteorites and doesn't happen to rocks on the moon. And so they can be older because once they formed, really nothing happened to them after that point. And that can't be said for rocks on Earth.
I mean, such an important point. And, Chris teaches, in addition to all the classes that I listed that I took from him, he now teaches an astronomy class that he made up as well. And so, Chris and I just been talking about, we're starting a sort of a planetary science or how to build a solar system, kind of a series on our podcast. And we're kind of going to start diving into this kind of planetary science aspect. And it's just it's such incredible science, the science of meteorite geochemistry, chronology, planetary science, like return samples from return samples from the moon, meteorites from Mars, and potentially return samples from Mars tell us a lot about what happened in that interval that we can't get out of Earth yet.
I love it when people are like, wait, planetary science and astrobiology or other, things about other worlds are like, why does that involve geologists? And I'm like, guys, they're big rocks.
That's right.
Yes, that's exactly right.
Okay, so we've established that the very oldest rocks that we date Earth age with are not technically Earth rocks, but the oldest Earth rocks are around 4 billion years old. Can you give us like a very brief list of maybe like the most famous oldest Earth rock formations and their approximate ages?
So, Jesse, do you want to talk about the Jack Hills, Zircon?
Yeah, well, Chris, we've talked about this a whole bunch. I mean, I'm curious what you would use for an analogy or a very simple explanation for like the difference here between the Jack Hills and, let's say, Acosta that we'll talk about next or something.
Well,
sorry, Chris.
The Acosta gneiss is what you have spent so much time dealing with, but it's a metamorphic rock, and that has its own difficulties in terms of dating that, because metamorphism, depending on what tools you use, and you have, as a geochronologist, Jesse, you have this massive toolbox, which I love, and I get so excited about talking with you about this. You have certain tools that can see through the metamorphism all the way back to the origin. But then sometimes we don't want that. Sometimes we want to see, when did the metamorphic event happen? So you're very comfortable with the age of the Acosta gneiss being 4+ billion years old. The Jack Hill zircons, that we're talking about sedimentary rocks here that have detrital grains. So we're not dating when the rock necessarily formed. We're dating the age of the grains or some of the grains that make up that rock. And those are really two different things. And we come up with, Jesse, what's the actual timestamp on those zircon grains? Because it's mind boggling.
Yeah, though the oldest ones, so they're detrital grains, so they're individual zircon grains. So it's a sand deposit. It's a conglomerate. It's a sandstone. So there's a whole bunch of different ages of these are zircon grains. They're sizes of sand, particles of sand, but there's a whole bunch of different ages of them. From 4.35 billion years old is the oldest. So a full 300 million years older than the Acosta rocks. But then there's other peaks. There's younger ones. There's 4.1 billion year old zircon grains. There's 4.0 billion year old ones. There's 3.9 billion year old ones. So there's a huge spectrum of ages from a single rock. The rock itself, the sandstone, was laid down, was deposited either 3 billion years or 2.8, somewhere in that ballpark. So the rock itself is younger. And this is the complexity I'm glad you highlighted that, Chris, because the complexity here is, so the Acosta gneiss, for instance, 4 billion year old, that's a magma that crystallized 4 billion years ago. That rock was metamorphosed 3.7 billion years ago, 3.6 billion years ago, 3.4 billion years ago, 2.9 billion years ago, 2.1 billion years ago, and 1.9 billion years ago. Those 6 or 7 different metamorphic events that happened to that rock. It's a tortured rock. And if I said this is a metamorphic rock, what's the age of the metamorphism here? What are the age of the minerals? Most of the minerals, it'd be 1.9 billion years old. But there's some primary minerals that record that pre-history. That's the age we talk about as the formation age. Sorry, Rachel, I'm just realizing we really didn't answer your question at all there on that long tangent we went on, did we at all?
Well,
what was it? You want us to distill down locations and numbers? Is that what you want that right now? And then we can move on?
We identified the Jack Hill zircons, which are in a sandstone.
Yep.
And
Sandstone conglomerate.
Acosta gneiss, which are in a gneiss, but are also zircon grains within the gneiss that represent the old grains. But every zircon in that gneiss, every igneous zircon in that gneiss will record a 4 billion year old history. We'll see that 4 billion year old, initial age imprint. Let me just add one more location to this, which is the debatable location, which is one that's potentially 4.25 billion years old. So 200 million years older than Acosta rocks, pushing that age limit with the Jack Hill zircon. But they're mafic. There's debate about whether that's a real age or an inherited age because they're mafic rocks. If not zircon.
It's based on an isochron. So whole rock, radiogenic isotope, geochronology, and actually what we call extinct nuclide geochronology, which is isotope systems that used to be alive and decaying and are now dead. And that rock is it's in the Nouveau-Agata Greenstone Belt in northern Quebec on the east side of Hudson Bay. It's exposed along the east shore of the Hudson Bay. So anyway, those are the three locations that are kind of in this conversation, I'd say.
Okay.
Yeah.
So on that, essentially not all three, 2 of these represent rocks that aren't actually 4+ billion years old. The rocks themselves are 1 to 3 billion years old, depending on which metamorphic date you just, which we'll get into what that means. But the grains within the rocks, the zircon grains and the Acosta gneiss and the Jack Hills, they represent the 4+ billion year old ages.
That's
so
right.
They are the grains that you are using your geochemistry on, which we'll get into, to get that 4+ billion year old age. So that brings up a question, because on my channel before I've explained this in a very simplified way. Essentially, the way that I explained how radiometric dating works, isotope dating works with metamorphism or metamorphic rocks is the metamorphic event kind of resets the geochemistry. And then the next time you try and go date that rock with isotope dating, you will get the date of the metamorphism, not the original, like you said, the original either deposition or igneous, formation, crystallization date of that rock. You are getting the later, younger age of when it became metamorphosed or tortured.
Yeah.
And so I've said that in a very simplified way, but like we've pointed out here, there are some grains, like you said, that don't get altered during that metamorphism and record that original age. So how is it that they do that?
So with zircons, you're going to use uranium to lead. In uranium to lead, you're going to be able to see through the metamorphism. You're going to be able to see through these events to go back to the original age of the zircon grains.
Editing Rachel here. I just wanted to add that when Chris says uranium to lead, he's talking about isotopes, uranium isotopes that decay into lead isotopes. Essentially, we use radioactive isotopes like uranium and their stable daughter decay products like lead to date rocks because radioactive isotopes decay at known rates. So we can measure the ratio of radioactive isotope to daughter isotope like uranium to lead ratios in a rock to determine how much time has gone by since that rock formed. In other words, since that magma or lava crystallized into a solid rock, which set those isotopes and kind of began that clock of decay. That said, metamorphism can reset the isotope decay clock. Metamorphism is just when a rock undergoes intense heat and pressure due to oftentimes tectonics. And so when we're having tectonic plates smash against each other and smush all these rocks together and cause them to undergo very intense pressure and heat, they deform, and sometimes their minerals change. And Jesse and Chris will both talk about this as we go on in the conversation. But essentially, this metamorphism, this alteration, can reset the isotope decay clock. And that means that when we come across that rock later on to date it, what we're actually dating is the metamorphic age. In other words, the timing of the metamorphic event, rather than the original age of when that rock formed in the first place. However, there are some minerals and some isotopes, for example, zircon containing uranium and lead isotopes, that are so robust during metamorphism that they actually preserve the original age of the rock rather than the metamorphic age, because they don't get reset during metamorphism. And this is what Chris is talking about here.
But there are other tools that you can use. You can use potassium to argon. You can use rubidium to strontium. So things like this may get reset by metamorphism because, like, for instance, with potassium to argon, you're talking about these gases that when you squeeze and heat a rock, those gases can get expelled out of the rock and released. And so then the clock gets reset using that tool according to when the metamorphic event happened, which is useful. We want to see that. So Jesse's going to use multiple tools in the same rock to look at different things. That's how he's able to see how you have these different metamorphic events in the Acosta, several torturous events that happen to this thing by using these tools. But using uranium to lead, though, he's able to see the original age of the zircon grains.
It helps to imagine what happens to a rock during metamorphism, let's say, for instance. And, when metamorphism happens to a rock, you're heating it up, you're squeezing it, putting it under pressure, the minerals are actually recrystallizing. So you're taking clays and you're turning them into starlite and garnet and then eventually kyanite or something like that. I mean, that's a metamorphic rock sequence. So the minerals are actually changing in this rock. They're breaking down, reforming. So you can imagine where if, a mineral grew and it had, Chris used a great example, potassium decayed to argon. And so there's argon trapped in that mineral grain, that feldspar grain. And then that feldspar grain got recrystallized during metamorphism. That recrystallizing grain would kick out the argon. So you're resetting the system there. You're kind of tipping the sand dial back over. Actually, you're taking the bottom out, draining the bottom, and then putting it back on the shelf. And so that's actually a beautiful thing. That's an amazing thing because it allows us to use different decay systems paired with different minerals. We have a bunch of different decay systems. We have a bunch of different minerals. We can pair many of the decay systems we can use from multiple mineral grades. So in the Acosta gneiss complex, I can measure zircon. I can measure uranium lead system in zircon, which is like the perfect system in the perfect mineral to see through everything because zircon's really robust. It doesn't get deformed by metamorphism. It doesn't get altered during metamorphism. If anything, new zircon grows during metamorphism. So it records this primary age. Apatite will not. Apatite will recrystallize. It'll lose its lead. Lead will get kicked out. So all the apatite in the Acosta gneiss sample I'll send you, Rachel, is 1.9 billion years old in uranium lead decay system. All the titanite is recrystallized and it kicked out all of its lead 1.9 billion years ago. And so it records a 1.9 billion year old age. So that's really amazing because you can use the same isotope system in different minerals and record different events in this rock's lifetime. So it's actually the power of geochronology, not a negative. The fact that these systems are sensitive to different processes is very powerful.
Yeah, I think you highlighted that beautifully because that is such a cool factor how this one mineral doesn't get deformed at all. So you could see the original date and then from minerals that get deformed more easily or maybe mediumly.
Yeah. No, that's right.
You can kind of see the history of metamorphic events after that original deposition or formation. And I think that's such a cool thing. I mean, it's incredible what we can, decipher from the whole complex of minerals within a rock. Because a lot of people
geochronology is just the best. I mean, I don't know why we do anything else for geochronology. It's just the best.
Hey,
we do a lot of other stuff.
Okay, all right.
Hey, Rachel, so one of the biggest misconceptions with Jesse's line of work, geochronology, is accounting for initial daughter isotope. I think that it's really important to address that the daughter isotope is what the original isotope decays into. What if that was already there?
I get that question in my comments.
Oh, yeah?
What's the answer?
Okay. All right. Let's say you're doing rubidium to strontium. Rubidium-87 decays into strontium-87. Okay. So when this happens and the crystals are growing and the crystals incorporate strontium, the initial strontium-87 that was there just because it was there. It's not there because of decay, but so is strontium-86. And strontium-86 is a stable daughter isotope. It doesn't get there. It's just nothing decays into it. And so if you can account for the ratio of strontium-86 to strontium-87, you can calculate how much the original rock or the mineral had. Yes. And that's the isochron method.
And the isochron method works great if you have you have to have multiple systems, either minerals or rocks that are genetically related, meaning they formed the same time from the same starting material. So if you have a single rock that crystallized at a given time and you have a bunch of minerals, you have feldspar, you have clinopyroxene, you have garnet, you have muscovite, and they all form at the same time from the same thing, you can use that. Those things can be used for an isochron if they all experience just that event and no other events. Then it's valid for an isochron. You get the age and the initial isotope ratio out of this isochron method. It's very elegant, very beautiful. If you don't have that, like we're talking about the early Earth, we often don't have multiple minerals or multiple rocks that have shared the same history. Then we have to turn to minerals that have no initial product isotope or daughter isotope in them. This is, again, the beauty of zircon. Zircon grows and it kicks out lead. It rejects lead. It hates lead.
That's what I had read is like it just doesn't fit it like in its structure. Yeah. Yeah,
exactly. So the uranium lead system's amazing because we have two isotopes of uranium that decay to two different isotopes of lead. Those two isotopes of uranium have different half-lives. And they're actually like the perfect half-lives. One of them is 700 million years old and has almost all decayed away. So it's very sensitive to early Earth. One of them has a half-life that's about the age of the Earth. So it's undergone one half-life. It's still around all over the place. It's like the perfect isotope system. Two of them that decay to two different lead isotopes. And then zircon comes in and it's independently at different rates, at actually perfect rates for Earth chronology, for chronology of things that are about 4.5 billion years old. And then we also introduced the perfect mineral, the mineral that takes in uranium, the parent isotope, the parent element, and kicks out, rejects the product or the daughter. I mean, you just could not,
and
if there's a higher being there.
Deformation.
Yeah, and it's so resistant to everything. If there's a higher power out there, that higher power gave us geologists zircon and the uranium lead system to do stuff with. That's like that. It's too perfect. It's too beautiful.
Yeah, we don't choose these, isotope decay rates. We just figure them out and then we use them.
Perfect.
And some of them are very old and some of them are, it's funny. Yeah. I often get asked like, oh, well, if carbon dating can only go back however million, thousand, like 60,000. It's one of my biggest pet peeves that people think like carbon dating is how we date everything.
Like, don't get Chris going. Don't start this. Chris's vein is going to start coming out his forehead. He's going to get all worked up over there about this.
Well, yeah.
You have to use isotopes that have appropriate half-lives for the age of the rock, for the age of the mineral that you're doing. Carbon-14 has a half-life of 5,730 years. Jesse knows you can't go back more than 10 half-lives. So you're talking about a maximum age of maybe 57,000 years on the far end.
Yeah.
Anything that's older than that, there's no carbon-14 left.
Yep.
So you have to use something that's age appropriate.
Yeah.
And that's the misconception that exists out there. We just use radiocarbon dating. That's the only tool we have in our box.
Yeah.
But it's incredible too, because the fact that we have these two uranium lead systems just with uranium lead, which is again, only one of these examples, the fact that there's two different half-life decay rates and you can kind of like double check yourself within the same mineral. That's really, really cool to like be able to cross check.
So cool.
Incredibly powerful. All right, this is my jam. This is the best conversation I've had all week for sure.
Wait a minute, Jesse. We talked for an hour earlier today.
Yeah, my point exactly. We didn't talk about uranium, lead, and zircon enough, Chris.
All right.
So to end off our conversation about the dating method specifically, I want to ask one more question because you guys also talk about in your podcasts a little bit about how these zircon grains, sometimes they contain multiple ages. So
Yeah.
can you talk a little bit about like zircon zoning and how you can actually even get that precise of ages within a single
Ooh.
grain? Very
Yeah.
How long do
briefly.
you have? You
How
just
long do you
opened
have?
the
Yeah,
box
exactly.
right now.
So how about this? I'll
Jesse,
give you a
you
short
have
answer.
2 minutes. Jesse.
2 minutes. All right. I'll give you
Yes.
2 minutes. If you want the like hour and a half answer, we have some cool images on our app, and we have like an Earth's Oldest Rocks audiobook, a visual podcast series on our app, the CampGeo app that has some cool images about this that kind of show what the zoning you're referring to looks like. And so you can see what it looks like and see what an analytical spot is. But again, let's go back to the visual of what happens to a rock while it's being metamorphosed. If I have a granitic rock that crystallized, has zircon in it, but it's mostly quartz, feldspar, biotite, maybe a little bit of amphibole, some other accessory minerals in there. The zircon, when that thing's metamorphosed, heated up and put under pressure, zircon, nothing's going to happen to that. So that initial zircon is going to remain just there. It's just going to hang out. What's going to happen is the amphibole is going to break down. The plagioclase is going to start to overprint and reset. The biotite is going to break down. Especially biotite and amphibole, those two minerals often have a little bit of zirconium, the element zirconium, in them. And when they break down, that zirconium gets released into the grain boundaries, kind of metamorphic fluids. The rock's kind of under pressure. So it's got some fluid in it. And what does that zirconium do? Well, it goes and finds the zircon and grows. It grows new zircon. It's kind of adding, bricks to a brick wall. It's building a new layer of bricks on a brick wall. And so you grow a new layer of zircon around the original layer. And this is really, really fine scale stuff. So we're talking thousandths of an inch or thousandths of a millimeter, like really, really small scale zoning, 10 microns. We have instrumentation. They're secondary ion mass spectrometers, or in my lab, we have a laser ablation system where we put laser spots that are much less than the width of a hair, like, 1/100th of a width of a hair wide. And we're blasting the little zircon grains with these laser spots and analyzing the uranium and lead isotope composition of those tiny little zircon grains. So
the core is going to always be the oldest, and it's going to get younger
typically
as you go out towards the rims. Yep.
Yeah, I think that is just incredible how one, zircons form and, preserve this history. And two, they can preserve like history within their own layers, their own grain, which is really incredible. Yep. Side note, can you guys hear my cat meowing?
No, I can't.
Okay.
We can't.
Good to
That's funny.
I feel like we have a good sense now of, the dating, methods behind this and what some of the ages of the oldest rocks on Earth are. So I kind of want to shift gears to the implications that Earth's oldest rocks have for kind of the evolution of Earth's early history and things that were going on very, very early Earth. This is where I get really excited about the conversation because this is the stuff I'm really interested in. But one of the things I remember hearing in one of y'all's podcasts was that zircons are minerals that are typically found in felsic or granitic rocks, which in other words means that they typically form in continental rather than oceanic type crusts. So like I've talked about this on my channel, and I've also talked about the fact that continental crust requires this differentiation process that typically today on modern Earth requires plate tectonics. And then I've also talked about that many geoscientists suggest that plate tectonics didn't really begin operating on Earth until around 2.5 billion years ago. So I think this brings up a really interesting question of, were the 4+ billion year old zircons forming in a different way? Was there very early continental crust that formed differently than it does today? And this is a question that we will be answering on part 2 of this discussion. So please go check out part 2 and stick around. That should come out the week after this. It might be out by the time you're watching this. But if not, and you're impatient, go check out all of their podcasts and their app. They talk about this. So if you want to go hear the spoilers, they answer all of these questions and more
Spoiler alert.
On their podcast. But still come back for part 2. We will be talking about essentially the implications of Earth's oldest rocks on our understanding of early Earth and how things evolved over that time.